Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the May 2023 IB Physics HL examinations. This is a paper 2 question and it's open-ended. Let's get started. A toy rocket is made from a plastic bottle that contains some water. Air is pumped into the bottle or into the vertical bottle until the pressure inside forces water and air out of the bottle. The bottle then travels vertically upwards. The air-water mixture is called the propellant. The variation with time of the vertical velocity of the bottle is shown. So here they've given us a graph to represent this scenario. The bottle reaches its highest point at time t1 on the graph and returns to the ground at time t2. The bottle then bounces. The motion of the bottle after the bounce is shown as the dashed line. Okay. Estimate using the graph the maximum height of the bottle. Okay. Part A. How do we do this? This is a velocity time graph, and we know the area under a velocity time graph is displacement, and the displacement up till t1 in this case represents the maximum height of the bottle. Why? Because t1 is the time at which the bottle reaches its maximum height. So if I can find the area of this curve up till t1, that tells me the height that the bottle reaches. So this is a triangle, so we can use the area for a triangle, half base into height. That will give me area, and we know this area in this case is also equal to a displacement. So let's put in everything we know. What's the base of this triangle? That's 1.2. And what's the height of this triangle? That's 12. And so if I put this in the calculator, I get 7.2 meters. Now that's the maximum height that the bottle reaches. Estimate the acceleration of the bottle when it's at its maximum height. Again, let's use our graph. We know that the slope of a velocity time graph is acceleration. And to find the instantaneous acceleration at the maximum height, I need to find the tangent at t1. Tangent, or the slope, is of course rise over the run. So what is the rise over the run at t1? We can say the rise is, we can take these 2 points right there. The rise is 2 and the run is 0.2. So I get the answer is 10 meter per second square. Usually for questions like these, they'll give you a range of values. So in this case, I think it's something from 9.6 to 10. You get any acceleration within this range, you get the right answer, because realistically you can take the slope from any point on this graph, and as long as you're mostly accurate, you'll get an answer in this range. So 10 is the answer I'm getting with the points that I used. Okay, part C. The bottle bounces when it returns to the ground. Calculate the fraction of the kinetic energy of the bottle that remains after the bounce. So fraction meaning division. What is the kinetic energy final over the kinetic energy initial? That's half m into v final square over half m into v initial square. The half m cancels, and essentially the ratio is just the ratio of their velocities squared. So v final over v initial whole square. Now that gives me the ratio of the kinetic energies. Now what is the final velocity? Well, the final velocity that I'm getting is 4.6, taken from that point right there. And the initial velocity, we can say is right there, is 10. And I whole square that. That's giving me, if I put this on my calculator, 0.21. And which approximately is 0.2. That's the ratio that I'm getting with the velocities that I used. Right, because this is the velocity right as it hits the ground, and this is the velocity right as it leaves. So yeah, that's what it is. The mass of the bottle is 27 grams and it is in contact with the ground for 85 milliseconds. Determine the average force exerted by the ground on the bottle. Give your answer to the appropriate number of significant figures. Okay, to solve problems like this, when something is in contact with something else, we have to use the principle of momentum. In this case, we can use impulse, J is equal to F delta T. Now we know that impulse is nothing but the change in momentum. So, and change in momentum is the mass into the change in velocity. So V final over the V initial is equal to the force into the change in time. Okay, how do we do this? We know the mass of the bottle needs to be in kilograms, 0.027 times what is the change in velocity? Well, the final velocity I'm getting is 4.6 minus of minus 10 right there, because this is as it hits the ground and that is as it leaves. So minus 10 over 85 milliseconds, so 85 into 10 to the power of negative 3 seconds. This will give me the force. So force, if I put this on my calculator, comes out to be 4.6 newtons. But keep in mind, they're asking for the average force exerted by the ground on the bottle. There's also a normal force that is being exerted, right? It's a net force. The normal force is mass into gravity. So we can say the normal force is equal to 0.027 times 10, n is equal to approximately, we can say, is approximately 0.3 newtons. So if I add up both of these, I get the F net is equal to 4.9 newtons. Because we need to consider that there's also normal force which is being exerted by the ground when the bottle is in contact. So 4.6 plus 0.3 equals 4.9 newtons. That's the average force. And finally, part D. The maximum height reached by the bottle is greater with an air-water mixture than with only high-pressure air in the bottle. Assume that the speed at which the propellant leaves the bottle is the same in both cases. Explain why the bottle reaches a greater maximum height with the air-water mixture. Okay, this is a really straightforward question. We know we can use momentum to solve this question, and we don't need to do any calculations. Momentum is mass into velocity. We know that the velocity is constant because that's what they say. It's the same for both cases. So the only thing that's changing between both these scenarios is the mass. The mass of an air-water mixture is of course greater than the mass of a only air mixture. And so with the greater mass, the momentum change of the air-water mixture is greater than only with air, is greater than the only air mixture. And the reason this is important is because change in momentum is impulse. Impulse refers to the force that's exerted for in a particular amount of time, right? So the greater the momentum change, the greater the force that's being exerted by the ground. So the greater the force is being exerted when the propellant is leaving the bottle, So the greater rate at which the propellant leaves the bottle, the more height that the bottle will cover. And so that's the reasoning behind it. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.